to have Professor Conan Leung from the Chinese University of Hong Kong to speak for us about this mirror symmetries. So Professor Leung is expert in many different kinds of geometries and physics, and he is also my PhD advisors. So yeah, please feel free to interrupt him and ask questions during his talk. Yeah, okay, Conan, please start your talk.
All right, so thank you so much for the invitation. It's my pleasure to give this talk here. And I was told by Yalong that the audiences could be mixed. And so I will think of, so anyway, I'm targeting this talk to the whole talk basically to non-mathematicians mainly. So the first half of the talk will be quite general, will not assume too much about mathematics at all. And the second half, I will probably just write on the computer, the notebooks, computer notebook, and we'll use a little bit more mathematics. So the first half is really a very general, give you a picture of what this subject is like. Right. So to begin, the way that I think about this is this subject has a lot of input coming from high energy physics like string theory and M theory and so on, mostly string theory. And there are lots of mathematics that are involved in this. And the mathematics involved, for example, those that I myself are very much interested in and involved are related to geometry and algebra. And then all these are related, interrelated to each other. Okay, so from the physics perspective, okay, and the high energy physics involved is called the superstring theory. It's a theory which decides to combine two, like a 20th century modern physics. To break through, one is the Einstein theory of relativities, which is a theory on the large to describe the galaxy and all these forces between galaxies. So the other one is the quantum theory, which is exactly the opposite, which are studying the physics of very tiny space, tiny particles. So these are the physics to study the forces among different particles. So one is on very large scale, the other is on very small scale. And amazingly, both of these theory, if you first learn it, it's just so counterintuitive. It's look completely different from the Newtonian mechanics, for example, the usual physics that we feel in our real life. Okay. And the mathematics that are involved are all kinds. Okay. The one that I will just use because at the moment I'm assuming that basically very little mathematics background for the audiences at the first half of this. So we'll involve like geometry, complex geometry, for example, complex number, many of those things. Okay, so let me just say a few words here. Geometry. Okay, so let's say that we look at the first geometry that we learned. Okay, the first geometry that we learned is we draw a triangle on a plane. Okay, and then we know that the sum, so this should be here. The sum of the interior angle of any planar triangle is 180 degrees. Or the other way of putting it is pi. Now, but if you draw the circle or this triangle, not on a plane, but on a like a balloon or ball, okay? In this case, I'm drawing it on the negatively curved. If you draw a balloon, then it kind of look like this, okay? If you draw a triangle on a balloon or ball, okay, it roughly look like this. So this then the sum of interior angle will be bigger than pi. Okay. In fact, the sum of interior angle depending on the area too. Okay, and it comes with this formula. So where k is the curvature, So for example, if you're on a plane, curvature will be 0. Okay, it's just flat. So whatever curvature means, it should mean that if it is flat, there's no curvature. So that's just pi. However, if you look, if the curvature on a ball will always be positive, and in fact, curvature is a measure of to the extent it can't look like a ball to second order. Okay, and then the curvature is like one over the radius of the ball. So the curvature will involve, and if this negatively curved, then the triangle will kind of look like this. That the sum of the angle will be less than 180 degrees or pi. Okay. So this is a shape of the positive and negative curvature. The one on the right, on the left, joint-like curvature equal to 1. The bigger the sphere is, the curvature will, the smaller the curvature is. Okay, just like the Earth, which look like a sphere. But the curvature is very small because it's, the radius is very large. So to us, it kind of feel like a flat land. Okay. And the one on the right-hand side is in fact, only at that particular point, the curvature is negative. It's difficult to write down. If the curvature is negative everywhere, then you cannot see it on L3. You can only see that on high dimensional space. So, but you can draw it to be negatively curved on one side. So basically, you see that curvature is measuring that on the left hand side is positive, is because if you go in this direction or that direction, they both curve in the same way. Okay, but on here, one is curving this direction, the other is curving reverse directions. So therefore, when you look at the product, it's kind of negative. Okay, this is how you see at that point the curvature is being negative. All right. Now I come to the mathematics that are involved. The first one is the complex number. Before complex number, then so we have real number. Okay. And then real number, you can draw it on a line, on a straight line. So the one that I draw here, like 0, 1, 2, 3. And there are a couple of very important numbers. For example, pi, 3.14159, and so on. And then the number e, 2.71828. E is defined by this. So for example, x is 0 or x is 1, then you get e here. Okay. And the number e is, so the number pi is important for the circle, sphere, and all those geometry. And the number e is important for the purpose of growth and decay. Like if you put money in the bank, how much money you get at the end of the years, related to exponential functions or the decay of particles that is controlled by this exponential functions. And the number e plays such an important role. It's called the natural log. Okay? And pi is related to the, for example, 2 pi is the parameter of a circle of radius 1. So those are real numbers. Okay, and then algebra that are involved. The first algebra that we learn in high school or even elementary school is to solve equations. So linear equation, you can solve it. And then the second one is like quadratic equation. So this is it: ax squared plus bx plus c equal to 0. Try to ABC is just some real number. Okay? And when you try to solve it, then you have the explicit formula. This x equal to plus b minus b plus minus square root of b squared minus 4ac over 2a. So if you all know that when you take square root, you can only take square root of a positive number. Okay. So for example, the square root of 1 is 1 or minus 1. And then we do not have the square root of minus 1 among real number. Okay, yeah. So what do you do? Okay, so that's why you need some imaginations. Okay, and then create a number, come from nowhere. Okay, it's not real. Okay, that's why it's called imaginary number. You create it and call this something so that the square is minus 1. Okay, so that the equation can be solved, and so therefore the quadratic equation can be solved. And then in fact more than that, many polynomial can be solved. Any polynomial of degree n will have n solutions if you allow to include this I already. So that you don't have to create any more. Just one I is enough. Yeah. So from this perspective, the beginning of a complex number, it sounds so artificial. Okay? As you will see later, in fact, in nature, in physics, this complex number is naturally there. Okay? From the perspective of Einstein theory, quantum theory, and so on. Okay. All right. So the following is probably one of the most beautiful formula in basic mathematics. Is all this number and all this mathematics operation that we learned in the beginning of mathematics, they all combine into one beautiful formula. E to the power I times pi plus 1 equal to 0. Okay, of course you have to say what that even means, e to the power I. Okay. So this is the same thing I just mentioned a moment ago, that because when we try to solve quadratic equations, we have to create I to show that I squared is -1, and this enough. Then once you have that, you can solve any equations, polynomial equations. You don't have to create any more. Okay, so let me just show you one example. Here is the one. Can you take the square root of I? The thing is, yes, you don't need to create J or something. Okay. All right, so here's the calculations. I'm just showing you that the square, you want to find something, the square is I. Okay, so this is it. You look at 1 plus I bracket square. So then you get, so this is just, you look at A plus B square. In general, you get A square plus 2AB plus B square. Okay, let me put it there. So you get 1, and then 2AB is 2I, and then B square. Now B is I, so I square is -1. So you get this term here, and then this cancel with that. You get 2I. Okay. So once you know how to take, so you know that 1 plus I squared is 2I. So therefore, if you divide by square root of 2, then the square is I. Okay. We're just indicating that you can take square root of I without much trouble. And in fact, you can continue to take any root and then any polynomial. And this is a fundamental theorem of complex number, basic algebra. So once you include complex number, this I, then you can solve any polynomial. Okay, so now the simplest beautiful relation between algebra and geometry is you can understand complex number, which is algebra questions, in terms of geometry. Okay, so while we have a real number, which is all this 0, 1, 2, 3, and so on. Complex number, you have to have I, so you cannot put it in a real line. So let's just put it in another direction. Okay, so you put it in R2, 2 dimensions. So in this case, this is 1, this is I. So when you sum, so this is 1 plus I here. Okay, so you draw it like this, and then so then you can put any complex number as a point on this 2 plane. Now the point of doing so is the geometry of the 2 plane. In fact, can tell you the algebra of the complex number. All right. So if you look at trigonometry, the basic one, you look at right angle triangle here. And if you put a number here, okay, and then the projection to the x-axis, this is the x-axis, and this is the y-axis. Okay, so this length is the cosine theta times r, and the opposite is sine theta times r. Okay, so therefore, if you do it like this, any x would be r times cosine theta plus I times r sine theta. Okay. Now, but if you use this formula, e to the I pi equal to plus 1 equal to 0, it was really basically equivalent to say that e to the I theta is just cosine theta plus I sine theta. So therefore, this number will be the same as that. So for example, if you look at 1 plus I, which is this number here, okay, and instead of writing 1 plus I, you can, in terms of so-called polar coordinate, the length, which is square root 2 here, the angle is pi over 4. Okay, so 1 plus I, you can write it as square root times this e to the I times pi over 4. And then if you look at the square, and then you just square both sides, and then this get 2, and then this exponential, you just pi over 4 plus pi over 4, you get pi over 2. Okay, and this one is just a 2i. Okay. So therefore, you can see that the algebra multiplications become the geometry of rotation on the plane R2. Okay, so that was the brief recall on review on the algebra and of complex number. Now next, let's have a quick discussion on what relativity tell us. Okay, it's a theory, Einstein theory of relativity. Of course, the famous formula e to the mc squared. V stands for energy, m is mass, and c is the speed of light. Part of the Einstein theory, this is so-called special relativity, tell us that, in fact, space and time cannot be separated. They has to come together. They play the role together. Okay. In what way? When time looks so different from space for us, okay, is that our space, our three-dimensional space, it look like this. Okay, so you can think about this three-dimensional space at a particular time, like 0, and after a while, time 1, and so on. We'll come back to this picture in a second. So together, it look like 4 dimensions. And but why would you write R31? Usually, we write R2, R3, indicating the dimension of the space with this superscript here. Okay, and the reason we write 31, you'll see that in a second. Okay, so this is the n-dimensional space, just a heuristic picture. What does n dimension mean? For one-dimensional space, it just refers that there's one direction you can move around. So this is like a real line. Okay, and n equal to 2 is the plane, because you get 2 directions, you can rotate, you can go around, and so on. And 3 dimensions, like our space now, is a box. Then you can have nodes and all this more complicated structure that are involved in 3-dimensional space. Okay, so 4 dimensions you can think about as 3-dimensional which are moving. So that's one family of 3-dimensional together become 4. Okay, and usually if you look at 3 dimensions, the length is usually just this: x squared plus y squared plus z squared, the square root. That's the length. That formula works in R2, R3, R4, any dimensions to measure the length in the usual sense. But in Einstein theory, the last dimension, the time direction, is completely not intuitive, because the length is negative if you are going along time direction. Okay, c is the speed of light, supposed to be very large. Okay, so that is why I write as R31, refer to 3 of those directions. The length is measured in some positive way, and then one direction, the length is measured in some negative way. Okay, the length of so-called length 1 vector is length -1 now. Okay, so the length can be negative. So that was a special relativity describing explaining that time and space are really not separated into 2 concepts. There's a combined symmetries called Lorentzian or Poincare symmetry. And general relativity, okay, is really explaining if there are like a big galaxy or very huge mass object. Okay, in fact, the space itself will be curved. In fact, I didn't put a picture here, but you probably have seen many of those pictures in many physics books and so on. And so the thing is, if you have gravitational force, that will force the space or space-time to have curvature, and in fact, vice versa. Okay, so there's this physical notion about force and the geometry notion about curvature is really the same. Okay, the space become curved because of the force, and the curve is the same as the force. Okay, but Einstein's equation tells us that the curve cannot be curved in an arbitrary way. Okay. The curvature has to satisfy a particular equations. It's called the Einstein equations. So here the energy momentum tensor is 0. So in this case, the Ricci curvature is 0. In general, it could be equal to energy moment. Could have another term on the right hand side. So let's say vacuum. So this is part of the curvature. In a way, this is some average of the curvature. Okay? You do not specify the curvature in each direction, but on some average sense, the curvature, which are called Ricci curvature, is 0. So this physics motivated equation turned out to be also the most important equation governing Riemannian geometry in mathematics as well. Okay. So as I mentioned, besides relativity, another subject that involves a quantum theory, and then these two theories look very different, and the string theory is intended to be unified theory to integrate all these two seemingly completely different type of theory. So this quantum theory now, instead of looking at very gigantic objects, look at very tiny objects. Okay, and some of those terms are called boson and fermions and so on. And in mathematics, those particles become some wave functions in quantum theory, and then the wave function I write as fx, okay, has to satisfy equation called the Schrödinger equation. Okay, so equations for some wave function called fx. X is the space time. Okay, so fx here, the first thing that we just mentioned earlier is this fx is necessarily a complex number. Okay, so this is the equation. Okay, and h bar is a very tiny constant, and if it is 0, then the quantum theory just behave like our classical theory. Okay. But that involves very complicated. So this is the second derivative. It's like a process of the function f. Okay. And then v is the potential functions, and e is the energy. Okay. And this equation has been driven a lot of development in modern mathematics, including a lot of analysis, calculus, and so on. Yeah. But the point I was making earlier is both the relativity that you can see here. You see that now, because you're taking a square root, and then some of the term here is minus. So therefore, it could be square root of -1. So therefore, in this case, the imaginary number will naturally come in. So even though at the beginning we are thinking about we create this symbol I, so that the equation can be solved, but now, in fact, in a way, you can think about that the nature already know that imaginary number is there. If you think about relativity is the right theory. And also here, that in the quantum theory too, the wave functions, to take a number is a complex, take the value is always has to be complex number to have a complete theory. So both the complex number or imaginary number come up naturally. Yeah. So the theory that involved in the string theory that I mentioned later also have a supersymmetry. Okay? in a way, which is a duality between, in this physics term, is these two type of particles, boson and fermion, which are look quite different, but they have a relation between them. If you go between one to the other, they turn out to be equivalent theory, which is what the supersymmetry is supposed to say. And sometimes people usually use this sexy word called the SUSY to be a shorthand of supersymmetry. And this behavior look very much similar to complex number. Okay, this should be imaginary number, sorry, not complex, just imaginary number. Imaginary number. Okay. Yeah. So if a real number, you times I, become an imaginary number. If you times I again, you come back to real number with a minus sign. Okay. In fact, that's more than it is true. In fact, I turned out that it's really the complex structure underlying the manifold, which has to be complex for the space to have supersymmetry. Okay. So this is not just a similarity. In fact, that's really the basic reason that later the space that we have to study are Calabi-Yau manifolds. Okay, so now you have to have string theory with supersymmetry, which will cause the superstring theory. As I mentioned, that was the theory supposed to integrate both general relativity and quantum mechanics, quantum theory. Okay. So it's a string and supersymmetry. And what is the string theory? It was designed to say that if you are observing in our space-time, observing a particle, it looks like a tiny particle. But if you magnify it by a huge amount, then if you look close enough, it is a string. So, but in fact, string can contain a lot more information than a particle can, because particle is just one point, and the string can itself can have string vibration, and string can even knots, and all kinds of things that could be involved in a string, which gives you a lot more mathematical structure. Here is something which string theory different from usual particle theory. So we are thinking about, as time goes, two strings come together and then form and then become one. Okay, they just glue together and then become one string. So this is when you're going to the right, you look like two strings coming together, intersect, and then become one string. Okay. But if you look at it from a space-time perspective, okay, and this would be just together, it's just very smooth surfaces. See, the thing here is at the moment that they intersect, and if you cut at this moment, they look like they intersect at that point. But if you together with the time, the whole thing look very smooth. Okay, you don't seem to have a particular, because space-time is really relative notions, and then there's no particular moment that the interactions take place, which is unlike in particle theory. If you replace the string by particle, okay, then this is a particular moment. You can't, any other places is very different. This is an exact particular moment that the interaction between these two particles come up. But once you become a string, then this is very smooth object. Okay. Now, and also in a particle or like a quantum theory, then you have all of this Feynman diagram. I mean, the particle come in and then interact and then split and so on. Okay, you get all kinds of singularity, like the interaction that we have upstairs here. And then once you replace the point by a string, then they look very smooth. And then all these different type of graph, Feynman graph, now just become this topology of a two-dimensional surface in mathematics. Okay, and now they all look very smooth. Now, the next thing that comes into the theory is how it turned out that when they try to describe the string theory, Okay. To have a consistent theory, so you have to have no anomaly. Nothing can go very strange. I mean, so if it turns out that that will force the dimensions, our space-time, to be 10 dimensions. So otherwise, the whole theory will have some problem that things are not consistent. So space-time should be 10 dimensions to have a consistent theory. But this is so counterintuitive because the way that we think about the world that we live is 3-dimensional plus time is 4 dimensions rather than 10 dimensions. And the way that to resolve this is the extra 6 dimension is just so tiny that we just usually in our naked eye cannot conceive it. Okay, and those are called internal space. So this is hypothetical. This is one way to relate it to our real world 4-dimensional field instead of 10. Okay, so this is a picture that if you look at a paper, like you look like a 2-dimensional paper, in fact, there's a very tiny thickness, which the paper is itself 3-dimensional. Okay, so this is the way that I'm drawing it. Now, instead of thickened, now this thickening is a 6-dimensional space. Okay. So our space-time is 3 dimensions plus 1, and a tiny internal space is 6 dimensions. So why do we care? Well, first of all, the point that eventually is the physics of the 4-dimensional space, in fact, are governed by the geometry of the 6-dimensional tiny space, internal space. And the supersymmetry in physics will force this 6-dimensional space to have a complex structure. Okay, so in our case, the space is 6 dimensions. So locally, the complex structure, because each complex space is 2-dimensional, because you have 1 and I. Okay, so 6 dimension, we have 3 copies of C. So we're at C3. So it's complex 3-dimension, which is the real 6 dimension. And also, you have to satisfy the Einstein equation with the Ricci curvature equal to 0. So you may ask, do we have such space? It's a very mathematical question. Okay, can you find all this internal manifold complex space, which has a natural complex structure, and then have a metric compatible, and then can find, which is also Einstein. Okay. In fact, that was solved in the 70s by S.T. Yao. He solved the Calabi conjecture. He says the following: if a space has complex structure, okay, and also so-called the first Chern class is 0, then in fact this Einstein equation can always be solved. Okay, and then also you can find this type of space. I mean, the space. Again, what are the space? The space that is internal tiny space in the 10-dimensional space, but the space has a lot of geometry governed by the physics of the 10-dimensional supersymmetry that has to have a complex structure and solve the Einstein equation. So if you already start with a complex manifold with metric, and then if C1 is 0, then you can solve it. Now, what is this C1 equals 0? This first Chern class is 0. This is really a topological condition. It's a necessary condition. This is if you look at the average condition on the Ricci curvature, and then you will force C1 to be 0. So this is a necessary condition. And the thing is, this is also very easy to verify. You can easily construct many space with first Chern class equal to 0. Okay. So this is not a strange assumption. It's a very natural assumption here, and then you know exactly when you can solve it when the space has complex structure. So you might ask, how about complex structure? Where can you find space with complex structures? And it turned out that you can just solve all those complex polynomials, as I mentioned earlier. Okay, if you have a polynomial of degree n in one variable, then you have n solutions. Similarly, if you have a polynomial with more than one variable, if you have like 4 variables. Okay. Then you always have solutions, and the solution will depend on 3 variables. Okay. And if the degree of the polynomial is 5, that is the same as the first train classes. So I'll mention that in a second. And then you can, as I mentioned, so this is very easy to arrange by just solving complex polynomial. And just write down the polynomial, and then you know that that space you have a complex structure, and you solve the Einstein equation. Okay, so that's a very important result, both from mathematics perspective, and also now because of this relation with string theory, is play extremely important role in string theory and mirror symmetry. And nowadays it's called a Calabi-Yau manifold or Calabi-Yau space. Here's what I said as an example. Right. So where do you get complex structure? Well, Cn is just many copy product together. It's a complex space. Okay, it's a very flat. This is completely flat. Okay, yeah. But then we want something to be compact, and so you have some way to compactify it. But once you compactify it, it's just like if you go from a plane, if you compactify to a sphere, then instead of curvature being 0, now the curvature becomes positive. Okay, so doing this compactification tends to increase the curvature. So the same here. Once you do this, you compactify it. In fact, this space is called CP4, called complex projective space. Will behave look like this, and then now become having positive curvature, non-negative curvature. So anyway, you get some complex space, but compact complex space, but positive. And now you want to have something on the average sense is zero curvature, the so-called Ricci curvature being 0. So, well, instead of solving the Ricci curvature 0, at least you can look at its average sense, which I just mentioned that you want the first train class to be 0. So what does that mean here? In this case, it just means that the degree of the polynomial is 5. So you see, very easy to track. Okay, so you just inside here, inside C4, you write down a degree 5 equation, so-called a quintic equation, quintic polynomial. I just write down one here. You can write down any others. Okay, and then if because of the fundamental theorem of complex number of algebra, you have all these solutions which behave very well, and then that is first train class equal to 0, a bit small. And that is then by the result of Yau, then this space is a Calabi-Yau manifold. It has Einstein equation that can be solved. Okay. So this one is a real 6 dimensions because it's you have originally 4 complex dimensions. You cut by 1 equation, you get 3 complex dimensions, which is 6 real dimensions. All right, so let's come back here.
Sorry, may I ask a question?
Sure,
so, thank you. I'm a mathematician and not very good at physics, but so I want to ask about the dimension of M. So it's 6, but so does it? So the fact that the dimension is 6 comes from physical observation or mathematical observation?
Okay, so in the beginning, okay, 6 is if you start to have a string theory, supersymmetry or not, okay, then you have to see whether you can observe things. So you have to eventually you have to do some. Let me see whether I can write it. Maybe just put this. Okay. In physics, usually that in quantum physics, you have to look at a very large path integral. So integrate some infinite dimensional space. Okay, I'm just drawing randomly, something like that. Okay, random. So you have to integrate some very large integral, mathematically not very well defined. And then eventually you want to replace by something that you can integrate anyway. But then the thing that you have to integrate, you have to be like a volume form. Okay. And if you are not in 10-dimensional, this thing that you can integrate does not really even make sense. It's not really in the right space. Okay, so then you cannot then the way that to compute what's the partition function, so-called the the probability of the observation, that doesn't even make sense. That's called anomaly. So that will have a particular dimensions, so that this thing that you can integrate is a volume form. That is the thing that you can really integrate.
Oh, I see.
And that forces the dimension to be 10. If without supersymmetry, it's so for 26. Yeah, and that is where we come out. And but after nowadays, so this is a, like, we don't know why, but anyway, it is just has to be like that. And then later we'll have a more better way of thinking about it, and I'll mention a little bit, and that's related to Ortonians. Okay, we'll come back to this in a second.
Thank you very much. Thank you.
All right. So very good. Thank you for the question. In fact, I welcome to have more questions. Just feel free to ask me any questions. And ask me physics question, good, but I probably cannot answer it. Again, I look at it from a mathematical perspective, because even though string theory is motivated from physics, but in fact nowadays it have a huge impact in mathematics. In fact, the development of string theory is both mathematics has a lot of idea coming from physics, and vice versa too. The development of the string theory also owe a lot to the development of mathematics. It's kind of a marriage between these two beautiful subjects. Yeah. All right. So let's continue, and this is exactly one of the points I'm making here, that in this 10-dimensional space-time, okay, our physics look like we are living in a 4-dimensional space, and this internal space is so tiny. However, the geometry of this 6-dimensional space, in fact, control much of the physics in our 4-dimensional space-time. Okay, that's why we really want to understand the geometry of this Calabi-Yau free fall. It's called Calabi-Yau free fall because it's a complex 3-dimensional, real 6-dimensional. Okay, so it's called free fall, referring to these three complex dimensions. Okay, the geometry become related to physics. It's really like Einstein theory that the geometry of curvature related to gravitational force, but now the geometry is much more sophisticated here. Now. And then they have this. Nowadays, you think about this is really duality. Okay, but at the beginning it was called mirror symmetry. From a physics perspective, this is a duality between strong interactions and weak interactions. So in a way, strong interaction is something which is usually very difficult to describe, and versus weak interaction, which is something much easier. Okay. This is but in fact, as I mentioned, that the physics in 4 dimensions is essentially reflected into the geometry of this internal space Calabi-Yau free fall. So the mirror symmetry should have a counterpart in geometry. Okay. And this has been leading to a lot of recent development in the last 2 decades. Okay. And has new mathematical predictions, and then leading to development of a lot of new idea and tools in mathematics. Okay. At the beginning of mirror symmetry, example is the enumerative geometry. Okay. But nowadays, the impact has been to everywhere in mathematics, just not just in enumerative geometry. So let me just say a bit about this enumerative questions. So you can see this is very classical mathematical questions. I'm just writing this to be so classical here. So let's just look at plane geometry on a two-dimensional plane. Okay. So the first one is to count number of lines. Okay. So first of all, given any 2 points, you have exactly 1 line. Of course, there's so many lines, but if you want to count line correctly, you want to count it to fix the boundary condition, like here. So to pick 2 points, and you have 1 line. Okay, so line is a degree 1 equations. How about degree 2? Okay, degree 2 equations is a so-called conic. Okay, conic refer to degree 2 curve. Okay. So because with degree 2, you have much more flexibility. So you can allow it to pass through many more points. Okay, so the right number of points is 5. So you can ask how many conic pass through 5 points. And the answer again is 1. Okay. But let's stop here, because the next thing type that you want to count things which are degree 3, which behave like topologically, look like a complex line. So those are called rational curve. Okay. So you want to count those rational curves which are of degree 3, okay, which are cubic. And the same, you have to impose the right condition to cut it down to 0-dimensional and then count them. And then the number of rational cubic passing through 8 points is 12. You can go on and then you can determine all this. Very classical questions in mathematics. And then a similar question, when look at, you can do this in any space. Okay, so here is the one that we mentioned. Okay, so this is a quintic threefold, Calabi-Yau threefold. So again, you look at this C4 or its compactifications, CP4, and then you write down a degree 5 polynomial quintic equations, and the zero set is this Calabi-Yau 3 M6. Okay, 6 again is only real dimension here, okay, but it's complex 3-dimensional. And then similarly, you just want to count the same the curve, number of rational curve in here of any degree. Okay, so degree 1 is just number of lines. It's 2,875. Okay, this is the number which has been computed many years ago. So this has been known for a very long time. Okay. How about degree 2? That was computed by Sheldon class. This is right before mirror symmetry. So when mirror symmetry come up, they test this one, and this is how many? 609,250. Okay. Now the next one is already very difficult to compute, and at the beginning, here's a quick story about mirror symmetry. Is at the beginning, mirror symmetry, they have a prediction of all this number. Why? What is the predictions? Why do you have such a prediction? Well, because you have a space. You're looking at what happened if you have nothing and then start to have a string and then ending with nothing. So it's like an interaction with nothing to get a string and then disappearing. Okay. And then altogether, and then this will be a rational curve. Okay. So therefore this counting this number is related to counting how many of such interaction can come out. Okay. And of various degree. So these could be very difficult. It's a quantum question. But then mirror symmetry will change it to another question, to another manifold, and then that becomes like a weak interaction theory. It's related to another mathematical concept called variation of Hall structure, that one can do a calculation there, and then get a solution of that equation there, and then transform it back to this strong interaction side, and then that gives you this prediction of all this number of rational curve of any degree. Okay, so at that time, they just generate a table up to degree 10 because the number is already so huge. Okay. So that they tell you all this number, and then they look at that. Then they want to check it whether they're consistent with mathematical computation. So they check this n equal to 1 is correct, n equal to 2 is correct. Okay, and so people try to compute n equal to 3 mathematically, and it turned out that the computation is so complicated. It was same type of computation called the Schubert calculus, but it's quite complicated in this case. And then the mathematicians, the group of 2 people that solved the problem, and then turned out that it's different from this number. Okay. And so therefore, at the beginning of mirror symmetry, that was in the early 90s, the first conference is really divided into 2 groups of people to understand this number. The physicists try to explain what they're doing to mathematicians try to explain what is all this variation structure, how to compute curve, and so on. And then, of course, all the mathematicians will side with the mathematical group that produced the number. And the physicists, I mean, because they, at that time, the people can't really understand each other. The language are quite different. And nowadays, after so many years, I mean, many people, know both sides of the story. Yeah. But at that time, they can only side with their own group. Okay, and then there's all this discussion between, well, whether you're right and you're wrong and all this. Okay, yeah. So the thing is, after the conference, a few months later, the mathematicians group, the group is mathematicians, that found out that the calculation is a gap, and then when they fix the gap, this is the number that they check with Proteus is correct. Yeah. So that is the beginning. That's why the mathematicians, you take the physicists very seriously, because now they really know what they're doing. Yeah. And then they become a huge industry to understand all this number and become a development of the Bloom-Witten theory, which is an important subject in mathematics. And this is only the beginning of mirror symmetry. As I mentioned, the impact to enumerated geometry has been huge. But nowadays, the impact to many other parts of mathematics in geometry, algebra, all kind, has been very, very deep. Now, I want to mention some further development is that, in fact, there are several types of string theory. Okay, they're all related to this 6-dimensional space-time. So just like a string theory, which string means superstring, in fact, the development of the string theory, the invention of the string theory, is to try to say that there are different types of like relativity and quantum theory, and there should be one unified theory. It's called superstring theory. Now, superstring theory itself has many different types of superstring theory. So should there be another? Should there be a unified theory? And that's the development of the M theory. Okay, and that in fact lives in one more dimensions. The M theory can have very special specializations that produce you all the different, seemingly different string theory, so that unify all the string theory. And then shortly after the development of M theory, Walther's group developed the so-called F theory. They tell you that this is really the ultimate theory, that more than just M theory, you cannot create any more. 8 is ultimate dimension to have the richest theory. Okay. Yeah. And so M, in fact, stands for the mother of all theory. Okay. And F stands for the father of all theory. So you don't have any other. Yeah. And then what is this number 8? In fact, it turned out that they are all, from a mathematical perspective, is related to this number called the octonions. Okay. And this is the largest norm algebra. Okay. So let me say a few words about this octonion. So let me say again what is the point here, is that for the physics, you gradually find out that the bigger and bigger theory, in fact, cannot be any bigger. The largest one from physics perspective is F theory, and its compactified space is 8 dimensions. And all this theory is really come from a geometry point of view, it's all come from quaternions. So what is quaternions? And that's also the biggest object in algebra object in mathematics. So you can see that there's in a way that the algebra structure of the octonion is really governing all the possible physics that we could have. So to begin, we have the real number, like 1, 2, 3, 4, 5. Okay, real number, we draw a real line. And then I mentioned all over that this talk about the complex number, like 1 plus 2i. So the complex number plays all this important role in general relativity, in quantum mechanics, in supersymmetry, everywhere. But in fact, in the 18th century, there is a development of what is the bigger algebra. It's that you have the natural property. So, and the next one is really the quaternions. Okay, in fact, the development of the quaternion at that time was a huge thing. It was just completely out of the blue. It's amazing at that time. That is a four-dimensional. It's a doubling of the complex number. So instead of I, you have I and J and K. In fact, this is a space with several complex structure I and J and K. Okay. In fact, shortly after the discovery of the quaternions, only a few weeks afterward, and they found out that you can continue to do that, and then you can create octonions. Okay. And this is 8 dimensions. Okay. Now, the octonion turned out to be the biggest possible norm algebra. Okay. So let me tell you what is a norm algebra. Okay. So you have your algebra, meaning that it's a real algebra. So you can you have all this element here, U and V. You can being algebra, you can take a product. That's what algebra is. Okay. But all the theory we look at is always have a norm. I mean, to measure things, just like Riemann and metric. We have to have a way to measure stuff. And so therefore you have a norm for each vector. Okay, a real non-negative real number, positive real number, and that's used. Yeah? And then this algebra structure, the norm structure, has to be compatible, meaning that you take the product algebra structure and then take the norm, or you take the norm and then you multiply them together, should be the same. Okay. If you satisfy this property, that's called norm algebra. And what are the possible norm algebra? This is it. Okay, there are only 4. There's no other. Okay. So given the first one is real number, the next one, the bigger one, is complex number. It has much richer structure, algebraic structure, because the imaginary number. And quaternion is even richer. You have several complex structure IJK related to each other. And then the largest possible one are octonions. So from mathematical perspective, octonion is the ultimate theory. And it turned out it exactly is the same as what the ultimate theory in physics, okay, that our universe is, that they're describing. The string theory in 6 dimensions, M theory in 7 dimensions, F theory in 8 dimensions, meaning referring to the internal space. And the reason of that is basically F theory is ultimate theory because the theory is all controlled and governed by the octonions. So in a way, this is the interplay between both geometry and or algebra and nature. Okay, so the octonion is the richest algebraic structure, and that's exactly the one that is describing our universe. Yeah, okay. So I think I stop here for the first hour. Yeah. Let me take some questions. So this is the first half, which are very general talk. No mathematics are involved. In the second half, I still are aiming to some people who are not really mathematicians, but I will say a bit more mathematics, involve more mathematics in this, and I will just write on the notebooks. Yeah. But before that, let's start. See, anyone has some questions?
Yeah, I think in the chart, there's questions.
Sorry.
Why does the norm takes value in real number? Why is real number so special? Why real number is so special? Yeah, because it's real, I guess.
Why the norm has to take value in? I mean, we want to measure things. You have to have a number to measure things, right? Because even if you go to complex number, then if you have something like a to complex number, then you will take the absolute value to go to the real number. Right? So in the beginning, you may have a so this is the kind of a simplest structure. In a way, you can think. Well, one way, I don't know is that a good answer or not, but anyway, one way of thinking, this is the simplest thing that you can have. I mean, that's why it's not a negative number. is the length inside complex number or the length inside quaternion number. Okay, so in a way, this is if you map to a complex number, in particular, you map to a real number. So you have this is the simplest among all. I mean, most of the time, I think, oh, I just have some way to measure a thing. You want to see which one is bigger, which one is smaller. That's why you get that. Yeah. And then usually have a norm is so that the norm is so that when the norm is 0, it's the same as when u is 0.
Mm-hmm. Yeah. So if there's no further questions, maybe let's take a 5 minutes break.
Right, that's good. Yeah.
Yeah.
Mhm.
Okay.
Yeah.
So let's
All right.
resume in 5 minutes.
All right.
Oh.
Okay, so I will just write on the notebook. So so I need to turn off this one. Okay. Okay. So just 1 second. Yeah. Sorry. Yeah. So we're thinking about a mirror symmetry. Or let's just say a particular type of duality. The simplest form is the Fourier transform or Fourier series. So let me recall how it's like. So if you have a function satisfy the property that x and x plus 2 pi. And what are those functions? The functions are the following. Here are examples. For example, cosine x, sine x, all this function has this property. Like this. Not very good. Periodic functions. Of course, all these are very important functions in mathematics, physics, engineering, and so on. Okay. And in fact, any such functions, you can write it as combination of cosine x or cosine 2x, cosine 3x, and x. So it can be cosine nx and then some coefficients, or it could be sine nx and some other coefficients for any n. Okay, and that is called a Fourier series of a periodic function fx. F satisfied that x equal to fx plus 2 pi. In fact, if you write, if you allow this to be complex number, that would even be better. Then you can write this as summations n from minus infinity to infinity, some complex number. So in this case, it's a and b are real number. If you allow complex numbers, easier, even easier to write. These are just e to the I n x. 2 pi I and x, yeah, times 2 pi. So that's it. Being a mathematician, quite often I will skip the 2 pi here, but in fact, it should be 2 pi times x. But for simplicity, let's just write in this, right? Yeah. So therefore, a function satisfies this property. So what does this property mean? Okay. So if you look at it as a real line, you can think about 0, 2 pi, and 4 pi, and so on, minus 2 pi. Now the function take value here, or here, or here, or here, are the same. Okay, so you can in fact consider this. You wrap around this from 0 to 2 pi, and then you wrap it back, and you wrap it back, wrap it back. Okay, and then that becomes a circle. Okay, of radius 1. Okay, and then the parameter is 2 pi. You just think about that. You have this very long rope, and then you keep on wrapping it together. Okay, and then this property that fx equal to fx plus 2 pi is exactly the same as saying that this is a map from x to c, or out or c in this case. Okay. Yeah. And so the statement is saying that this is information is the same as you can write this as a summation of n from minus infinity to infinity, Cn e to the inx. Okay. So this is the number Cn. So what are the possible n? These are the integer. N is all the number here. And then you get a complex number, Cn. Okay. So this function I call it f hat. Okay. And then vice versa. So this expression is just saying that a function on S1 and a function on the integer are equivalent to each other. Okay. In fact, with more care, more naturally, you should think about that this is instead of looking at R over 2 pi z. Okay. So this is a function on here. Is related to function on this one, which are equivalent by this Fourier series. Okay. If you make the scale change to be times R here, and then this will be 1 over R here. That becomes the natural relation between them. Okay. And that's quite important. That means that on one side, you are looking at from 0 to R, maybe 2 pi times R, and then 4 pi times R, and so on. And then the other side will be 0, will be smaller now. 1 over R, and then 2 over R, and then so on. Okay. So this has a relation between a large circle and a very small circle. So I have some technical difficulty here. Let me just switch the computer to another one to use the screen. So this one's, bear with me for 1 second. Let me use this one. Screen. Just 1 second. Yeah. Okay. Let's try to see whether this one is okay. Just 1 second.
Yeah, sorry, maybe you forget to unmute yourself. Can you hear me?
Maybe he doesn't. So maybe can you contact, write him on the chat? Or
Yeah, let me try it.
Can you hear me now?
Oh, okay. Yeah, we can hear you now. Yeah, but
Yeah. So another way of thinking about this is another way of thinking about duality is if you have so we are thinking about R over RZ versus R over 1 over RZ. Okay. What is this relation? Okay. You can think about a high dimensional setting, which will be if you have a vector space V, which could be like Rn. Okay. And then mathematics that has a dual space V star. Okay. V star is just the order consists of all the linear map from V to R. Okay. And a duality is a property that if you do it twice, you get back itself. Okay, so you go there and come back, you get back itself, and that's what the duality is. So among this, other thing is if you have a subspace, linear subspace in P, you can look at a dual subspace. This is called P per, which are all these elements here, which vanish on P. Okay. It also has this duality behavior that if you apply twice, you get back itself. Okay. Now, another type of basic duality in mathematics is again, if you look at this vector space, this is similar to what we just had, is you can look at the lattice inside. But in general, as I just mentioned a moment ago, the lattice could have different size, but abstractly, it just looks like a Cn inside Rn, but it can be bigger and smaller. Okay, if you have a lattice inside, and then you again can look at the dual lattice, which by definition are those linear functional. When you restrict to the lattice, this sit inside integer. Okay. And it also has a property that if you do it twice, you get back itself. Okay.
Oh, excuse me.
So we have several
Can I ask a question?
behavior. One is we look at a
Excuse me.
subspace,
Can I ask a
or you
question?
can look at its lattice. So example would be Rn.
yeah, I think it seems
at a
he
subspace could be
cannot hear
Rk.
us.
Right.
Then you can look at its lattice, which is like this.
Yeah, it's
C,
weird,
oh, sorry, just
but
N, which look like a Cn. Okay. Well, but thinking about Rn overs, you can also look at the circle, as I just mentioned, which is the
so Yalong,
R,
are you
over C.
writing to him or?
and then you can do a similar thing.
Yes, already.
Or in
Okay.
general, you just
But
look
I'm
at
not
this
sure
vector
whether
space quotient by the lattice.
whether he will.
So this is
see.
just which we call it torus, and the behavior in high dimension, it just look like n copy of the circle together. Yeah.
Can you
Right.
hear us?
So, so this will, you can look at a torus, and then you look at the dual torus. And this is called a T duality. And then a Fourier series that I mentioned earlier, in fact, can be interpreted as a special property about this T duality between the behavior of the torus and the behavior of a dual torus. An example of this would be a circle of radius r would be due to the circle of radius 1 over r. Okay, and that this kind of duality, for example, will include what I just mentioned as the Fourier series. Okay, and mirror symmetry was a mysterious duality at the beginning, as has all this prediction on the enumerative geometry at the beginning, as I mentioned, until in the 1996, 97, Strominger, Yau, and Saslow has a interpretations that the proposal that mirror symmetry should be just a T duality. Okay, And in fact, this is the title of the paper. Just mirror symmetry is T-duality. Okay. So why is that? That's what I'm trying to explain to you today. Yeah. So mirror symmetry is interchanging strong and weak interactions. For mathematics, mirror symmetry is interchanging so-called A model to a B model. Well, what are they? Well, these are complex geometry. And these are symplectic geometry. Sorry, symplectic geometry. Okay, so complex geometry is easier to say. So in general, a space could be like Cn. Locally, it's always Cn. In complex geometry, you might want to look at some subspace, which is Ck, where k can be 0, 1, 2, 3, 4, 5, up to n. Okay. These are complex subspace. In general, for a curved manifold, then you could get this type of subspace locally. Okay. But on the other hand, in symplectic geometry, it's quite different. Symplectic geometry, the space is like cotangent bundle of Rn. You can think about this is Rn plus is still space. Anyway, the subspace you should look at is always a half-dimensional subspace. For example, would be kind of like Rn sitting inside Cn, in fact. In general, these are called Lagrangian subspace in general. And first of all, you see that, oops. Did I lose something?
Yeah, can you hear us?
Can you see it now?
We can. I think you cannot hear us.
Hello? Oops. Oops.
Can you hear us? Sorry.
Okay. So if you have a subspace S here, and then you will have a subspace S here, IS. And then so therefore this side you will get S and IS, which is a subspace here. So this is S tensor with C. Okay. You have a complex subspace here of various dimensions depending on S. Okay. But in mathematics, it turns out that if S is naturally a subspace in V, then the quotient is not in V. It's a quotient space, let's call it Q. Then we can look at still sequence. Then Q does not sit inside V, but the dual of Q sit inside the dual of V. Okay. So therefore, on this side, A side, you will look at S is still here, but upstairs instead of S, because now the fiber is still space, you will be looking at the Q star. Okay. And then together, this one is always half dimensions. This is dimension 2k inside here. If S is dimension k, S plus S is dimension 2k. But S is dimension k, Q is dimension n minus k. So therefore, this space is always a half-dimensional subspace. And in a way, this is a simple space of interchanging this n-dimensional subspace and any of this 2k dimensional space between Lagrangian in symplectic geometry and complex cycle in Cn. And this, in a way, is the most basic one. Okay. So, and what is the SYZ philosophy? It's the following. Okay. If you start with a space called X trap in B side, which if you are related to X on the other side, on the A side, these two spaces are mirror to each other. Okay. So the geometry and the physics should be related. For example, you look at this kind of complex cycles, as I just mentioned earlier, that should correspond to some Lagrangian cycle. These are always dimension n, these are dimension 2k. Okay, these are complex dimension n. Okay, both are complex dimension. And these two should be related to each other. Okay? And it's difficult to see what are all these possible space, except one particular case. When K is 0, that is easy because like 0-dimensional space is just a point. Okay, so in fact, more importantly, is the space itself is the union of all the points. Of course, I mean, a space is the union of all the points in the space. Okay, it's a collection of points. Okay? Right. So if this is the case, what should be the mirror object in A side? Because on B side, the dimension can be even 0 dimension, but on the A side, everything is half dimension. So a point here should correspond to a half-dimensional space. Another point here will correspond to any half-dimensional space. And all those points together should fill in this space. So the other side, all this Lagrangian subspace will also fill up this other space. But you will see that this will not make sense because you get too many points here because each space is already n-dimensional. And then all this space should not intersect, which is just reflecting the fact that any 2 points, they either equal or they don't intersect at all. So you should have the whole space foliate become a union, disjoint union of this half-dimensional subspace, Lagrangian subspace. Okay. In fact, whenever that is the case, you get an integrable system. So all this Lagrangian space should really be just a torus. Okay. Furthermore, as I just said that, in fact, so each of this is a torus. It's a family of torus. Okay. Furthermore, in fact, you have more points than having torus because you get 2 n-dimensional on the right-hand side and you want an n-dimensional family, n-dimensional family on the left-hand side. The thing is that each of these torus can have a non-trivial gauge. So this has you have a U1 gauge, which mathematically is a flat U1 connections or the gauge field on T. So that you can have some twisting on top of each torus. Okay, and the amount of those is also n-dimensional. So what I just said is a point here should correspond to a torus here together with one of these gauge field. Okay, another point here different point could correspond to a different torus, or it could correspond to, so it could be another point here. It's also possible to be the same torus, but a different gauge field on top of it. Okay. Now, here's the most important point is if you look at all those flat this U1 gauge on the torus, this whole collection up to symmetry, up to equivalences, this is the dual torus. So the earlier description of the dual torus has a geometric description. They're just once you fix a torus, is all the flat U1 gauge field on the torus. Right? So therefore, now if you look at you can look at many points. They correspond to the same torus, but different gauge field. So you look at all the gauge field. Okay? And then what are that collection? Well, this is exactly the dual torus. This is just what it said. You look at all the points here, which correspond to on the other side, the same torus with different gauge field, and this whole collection is the dual torus. Or in conclusions, that this has all this torus with gauge field, and the other side, you just get all the dual torus. Therefore, the prediction is the SYC perspective is if X and X track are mirror, okay, then the analysis that I mentioned is only asymptotic analysis. It's only related to the like a semi-classical limit. So sometimes called the last structure limit. It's a limiting behavior. in this limit, then they have the following structure, that both of them will have a torus vibrations over the same base space. And then the torus are just due to each other. Okay, so the space itself is just interchanging a torus to a dual torus in this limiting version. And then the next thing is then we can apply this type of Fourier transform earlier about not just the torus, and that is the function theory, and that's supposed to give you, okay, then the Fourier transform along all this torus fiber is to expect to give you the transform all the symplectic geometry on X to these are called the S by C transformation to the complex geometry on the dual space. Okay, so this is the basic of this S by C proposal, and I was explaining this type of thing. And here's the example. Let's just look at the simplest case. Here is just Rn. Okay, the fiber is Rn star. So this is the A side. Let's just call this V, okay? And this is V star. And then on the other side, then we are just looking at V plus IV. Okay. But this is not a compact space. To look at a compact space, we quotient this by the lattice lambda, and this quotient by the dual lattice. Okay. So therefore, you get a dual torus vibration. This is T. This is T star. Okay. So this is the space X, and this is the space X trap. Okay. So now, if you look at a subspace here, which is the S, and then you look at the corresponding Q star. Okay. As you remember, when S is the quotient by the corresponding lattice, okay, and that will be the Lagrangians, okay, because as I mentioned earlier, when S is a subspace in V, the quotient is called Q, then Q star will be a subspace of V star, quotient becomes S star. So therefore, the S plus Q star become a subspace in V plus V star. Okay. And that's the Lagrangian L that we're looking at inside this X. Okay. And then if you look at this SYC transformations, what we did is we don't do any transformation on the base, so just fiber by fiber doing T duality. And the fiber Q star here, and then the Fourier transform in this case is just look at all the flat connections which are trivial on Q star. And what are those? Those are exactly the S. Okay. So that exactly. So the Fourier transform, fiber-wise, this is a T duality, is a fiber-wise Fourier transform. It's exactly giving you this correspondence between Lagrangians, L, which is S plus Q star, to S plus S. Okay, so this is a Lagrangian cycle, and this is a complex cycle. Okay. So all this space, I should mention that a couple of remarks here is that our space X has to be a Calabi-Yau manifold. Threefold. Okay. and maybe I should say a few more words of what that exactly is that our space should have X, which has a Riemannian metric and has a complex structure J. Okay. And then remember, we also want the Einstein equation, which is curvature equal to C. Okay. Yeah. And by Yau's theorem, this is come from a topological condition where C1 of X is 0. Okay. But what is the symplectic geometry? Is that, of course, the complex geometry is right here. J gives you the complex geometry. Okay. And symplectic geometry come from the following two forms. You combine G and J, you can construct omega here, which is this combination of G and J. Okay. And that gives you this omega is a symplectic form here. And symplectic geometry is started from the study of quantum mechanics. So this is the symplectic geometry. And the mirror symmetry is really these two types of geometry got so very different type of geometry got exchanged, but not on the same space, but on a dual space. As I mentioned, it comes from T duality. Yeah. And C1 equals 0 can be interpreted as having a complex volume form. Okay. So as I mentioned, that in fact this is 6-dimensional theory, string theory. Okay. But the ultimate theory is really come from 8 dimensions. And the Calabi-Yau threefold will be replaced by a more general so-called Calabi-Yau fourfold, because now it's 8 real dimension, complex 4 dimension. Or it could be more general, something called a spin-7 manifold. But the most important class of those which you can really work on is really Calabi-Yau fourfold. And there has been a lot of work on so the threefold and fourfold theory should be combined together. Okay. And there are lots of recent study of Calabi-Yau fourfold geometry. And especially you can see, if you want to know more, you can ask Yalo. He is the expert in study this geometry for Calabi-Yau fourfold, which is a much more difficult question than what we learned in Calabi-Yau threefold. A lot of the mathematics are developed to study the geometry of Calabi-Yau threefold in the last 2 decades. And only very recently, in the last 3, 4, 5 years, that we start to get a better grasp on the geometry of Calabi-Yau fourfold. And I think it's still a beginning phase of our understanding that. And that is part of the F theory. So this gives a very brief introductions of some of the concepts which are involved. This is a very gigantic and huge subject. I hope that in this talk, I'll just give you some impression of how it might look like. If you have some other question, feel free to ask. There are various parts of the theory involving like Dirac category, Fukaya category, homological method, and algebraic geometry, and so on. I only pick out some of them that give you a flavor of how this theory is like. Let me stop here and then take some questions. Yeah.
Okay, may I ask a question?
Yes, yes, please.
So in the last minute of the first part of your talk, you mentioned that F theory is related to the octanion, right? And yes. How does octanion comes into play in this story, in the Calabi-Yau fourfolds?
Let me see how to say it. Okay, so let me say describe the one in the middle first. So you have an octonion. Okay, so just like the following: inside complex, like a real complex quaternions. Okay, quaternions split into the real part and the imaginary part of quaternions. Okay, the same as octonion split into real part and imaginary part of the octonion, which is 7-dimensional. Okay, yeah. So if you're in an oriented theory, if you pick out a one direction, then it's become the 7th-dimensional theory. This is related to the M theory in this case. Okay, yeah. Let me say a few words about that first. Yeah, because it's easier to describe this 7-dimensional theory related to the octonion directly. Yeah, because in a way it's kind of oriented in some way. Okay, so so this is a G2 geometry, or it's also considered to be the octonion geometry. It's octonion geometry with orientation, basically. Okay. Orientation in the octonion sense. Okay. Yeah. So this is a 7-dimensional space. If you think about the 7-dimensional space, that's just in the linear theory as the imaginary part of the octonion. Okay, then it has a product structure by saying that if you have two imaginary octonion, you can take the product as the octonion and then look at the imaginary part. Okay, that's definitions. Why do I want to write in this way? Because if you look at it as a quaternion, this direction, this is our usual vector cross product, vector product, just like this, UV times psi theta. All right? This is UV and theta. So the usual vector product in R3 is really part of the quaternion geometry. So in fact, a lot of 3-dimensional topology and geometry is related to quaternion geometry because it's come from, you have a vector product which you don't have in other dimension. In the only other direction that you have this vector product is coming from the quaternion geometry, octonion geometry in the 7 dimensions. Okay, so a space, a manifold, 7-dimensional manifold, Riemannian manifold with this product structure on each tangent space. That's a definition of a G2 geometry. You can say the same thing in 8 dimensions, but the product is slightly more complicated. That is the octonion structure. Okay. But let me say that again, how is this related to the Calabi-Yau 3 now? The thing is, if you pick a direction, let's say you split this is in a 6-dimensional plus 1 dimensions. Okay, that means that among those, you pick a particular vector. So call this direction, call this W, let's say, maybe call this W, okay. Okay. Yeah. Then you can have a U cross V. Okay. Now whether you have W or not, okay, so you can write down U as some components without W. So just write it as a U1 plus a number times W, and then V as a U2 or V1 plus a number times W. Okay. So the vector product now will split into part which come from U1 and V1, and then some other part is involved in the R. Okay. And then this splitting is just saying that the product structure now becomes the holomorphic volume form and the symplectic form on this 6-dimensional manifold. And that is the Calabi-Yau structure, Calabi-Yau 3 structure. And this does not work in any other dimensions. So given a Calabi-Yau 3 structure, in fact, you can use that to recover a octonion structure with 1 trivial directions. Okay. And the point is, there are lots of geometry for Calabi-Yau manifold work in any dimension, but the more subtle ones, like nowadays people do like the Donaldson-Thomas theory and many of those, it only works for Calabi-Yau threefold. And the reason it works for Calabi-Yau threefold only is all because this Calabi-Yau threefold, this Calabi-Yau structure in this dimension is really a special set case of the octonion geometry. Okay.
Mhm.
So therefore, Calabi-Yau geometry is very rich, but Calabi-Yau free geometry is much richer. And similarly for Calabi-Yau 4. Yeah. And they don't have it for any other dimension. Let me just give a analogy here. Okay. If you have a Calabi-Yau 3 or Calabi-Yau 4, okay, or any other Calabi-Yau n, okay, well, I just want to say that these are different. So these are complex dimensions, 3 and 4 and n dimensions. Okay. And then if you look at this symplectic geometry, the Lagrangian here will be dimension 3, dimension 4. There's a half-dimensional submanifold and dimension n. Okay.
Mhm.
Now, for example, in all this case, we will have to include a flat bundle, flat connection on top. Flat connection on top to be this flat gauge theory. Now here's the indication why Calabi-Yau 4 is much more interesting. Here we could include anti-self-deal so-called instanton connections on this, as in the Donaldson theory. Okay. So the way of Calabi-Yau, so the Calabi-Yau 3-4 versus Calabi-Yau n, you should view it as a complexification of like a 3-dimensional Chern-Simons theory, 4-dimensional Donaldson theory, versus in any dimension, then you only get flat connections. We don't have a much interesting theory about all this connection. Only a dimension in 3 and 4, the space of vector bundle become much more interesting. In dimension 4, you can get anti-self-deal. In dimension 3, the flat connection is a very rich theory, giving you Chern-Simons theory. And then now we're just looking at its complexifications. And that's also why you see that this is a quaternion theory, and this is the Ottonian theory. So the usual low-dimension topology, whereas people study 3-4 manifold, is really, you can view it as a study of the quaternion geometry, of quaternion geometry. And then now we are upgrading to understand the Ottonian geometry.
Ah, I see. So yeah, thanks. Thanks to Yaron, I have listened to several talks about Calabi-Yau geometry, but this picture is very beautiful. Thank you. Yeah,
Yeah.
I have seen this for the first. Maybe at least I recognized for the first time. maybe other speakers might have given this in a different form, but this is quite.
Well,
nice.
this is why this analogy will give you a global perspective. Why this is in a way the ultimate theory, because in the 80s, I mean, of course, Chern-Simons theory and Donaldson theory is kind of dominating a huge part of geometry, and now we are looking at complexification of this whole subject. It's much richer, and this is also the ultimate theory because we cannot go any further because the Ottonian is the largest algebraic structure.
Yeah, so actually I'm a number theorist, so I am living in a number in the field world of numbers. So yeah, if you say that the Ottonian has a very specific algebraic structure, then yeah, it's quite convincing for me, and it's quite interesting. Thank you.
Yeah. So, and also you see that this structure is reflecting. So here is one thing is that if we go from complex number to quaternions, quaternion has a lot of structure, but it also loses some nice property because complex number is commutative, xy equal to yx. But quaternion is not. I times j equal to minus j times I. It's not too bad, but it's not a field anymore. But still a lot of things you can continue to be quaternion. But once you go to Ottonian, you seem to lose a lot of structure. It's not an associative algebra. AB times C is not A times BC. A lot of what we do for quaternion does not work in Ottonians. So it seems that it's not so interesting. However, Ottonian, once you lose this, those structure is reflecting in so-called chirality. If people study Ottonian algebra, then you see that the chirality structure is everywhere. It's extremely rich, and then a lot of very subtle property. And that's also reflecting to why our study in Calabi-Yau 3 and Calabi-Yau 4 for geometry is so much richer and also quite different from 3 and 4 manifold. It's in a way reflecting this phenomenon of you lose the associativity, but you gain different type of symmetry called the orderarity, called the chirality.
I see. I see. Oh, yeah, that's very interesting. Yeah, thank you very much.
Yeah, is there any other questions?
Well,
Yeah.
if
So
you
may-
don't ask me now, it's not too late, and you can always ask Yalong.
Yeah, thanks a lot. Yeah. So yeah, if there's no further questions, so let's thank Conan again for his wonderful talk.
Well, thank you so much.
Yeah, thank you very
Of course, it
much.
will be better if I can come someday in person.
Yeah, sure. Yeah, because I think it's now quite easy to visit. Yeah, it's possible to visit Japan now. Yeah.
Well, it's not possible to come back to Hong Kong. That's a problem.
Really?
Yes, if I go to Japan, I have to quarantine for 3 weeks after returning to Hong Kong.
Oh, I see. The same as mainland China.
Yes.
Oh,